integrated circuit 10, digital circuit, logic element, NAND gate. Okay, all the logic design in IC chip started with NAND gate. NAND gate is like a TTL or STTL. STTL is like the Schottky. The Schottky diode will be here and holding this point so that transistor doesn't get saturated. And sometimes we write transistor like that because Schottky diode is integrated into the transistor. Okay, so what happens is if one of them goes low, this pull down here, this turn off. So this goes up, output become high, right? So only one of them make output high. That's a NAND gate. So its logic operation is A, B, not, right? But later we started using a CMOS, advantage of less current for each gate, and the surface layout got small, so we could integrate the large number of gates very well. Now this is example of CMOS, and if you look at this logic, if one of them A is high, is shut off the gate and on the other one, so output become low. So only one of them is sufficient to make output opposite. So this is actually NOR gate, right? So the both you don't have to have a both high to have this X change. It's only one of them go high, then output become low. Okay, so is there any difference? Would it make any difference in logic design? It's actually not. Okay, you learn in the computer science logic design, right? And there's the Morgans Theorem, and what's happened is if you have a NAND gate, you can expand to A, B, C, D, not, or X, just this is not A, right? Then you can express any kind of logic. Say you have a X equals ABC, BCD, ACE. Then what we do is not, right? The inside, it's going to be multiply of these terms and not, right? According to the Morgans. So only NAND gate is sufficient to have this expression. This is example A, B, C, NAND, and C, A, let's see, C, B, D, NAND, and this NAND all together goes to another NAND, which is this guy, right? Then you get X. And same is true for NOR. Okay, you can expand any expression, everything using only NOR. So this is called the basic logic element, and you can design any kind of logic using only basic logic element. So what we need is, in a digital integrated circuit design, the basic logic element like NAND or NOR. For example, if it's ECL, we have emitter coupled, and you put another transistor here, then become this is the gate. And this one, if one of them high, then current flow this side, and this output will be low. So it's going to be NOR. But ECL has also this opposite polarity, OR. You get two results at the same time from the single logic. Okay. So this goes here, this goes here. So depend on how you construct the logic element using transistor, so you can have any kind of logic design. And you may say, how about latch? It's not exactly logic design. Well, it is. So what happened is we have feedback logic like that. Okay, and if this guy and this guy is high, so you know this is high, low, so this is high and low. So what happened is, let's try again. If this is low, this is gonna be high, and this is high. Both are high, this goes slow. So it stays that way. So it can stay on the opposite side. Alright? If this is high, so the high is gonna be low, and it's low, so it's gonna be high. Then it stay. So this kind of feedback has a two different state. Either this can be, it can be high or low, depend. Okay. Then how do you control that? Okay. You have a control gate, means latch signal. When latch signal is high, then the A goes through, but A is inverted here, so it's going to give either high low or low high, and that determines the state of the latch exactly. Okay, and once it's determined, you bring this low, then this both become high, and the latch state stays same. It's like a memory, right? So latch is a memory, but constructed by logic. The real memory chip, we describe that later, use a different mechanism. You can't afford to spend so much gate to make just one bit. Okay, you need the gigabits of memory, so they simplify very clever way to have a memory one bit. But this is a logic memory. The memory element made by logic is called a latch. Now there's a flip-flop. The reason why we need a flip-flop is you have a clock and you want to make it like, okay, it store the data at the rising edge. Latch is level control. When this is low, it's holding. High, it's not holding, and low, it's holding. Okay, but you want to make it edge control. When you want to make it edge control, then each clock cycle you can update the logic into the flip-flop. So this is latch and latch, and A is driving, negated A, the latch, and the latch output directly go to another latch. And trick is to have a latch control in the opposite polarity into two different latch. So what's happened is, say when this goes high, right, then this guy accepts the data here, maybe high and low, right? And when it goes low, then this guy accept this data here, and this guy start accepting the new data from A. Okay, now while accepting data from A, this guy hold the previous half cycle data here. So overall output is gonna hold entire cycle the data, and next edge the new data starts showing up. Okay, so this is like registers in a CPU or all kind of register. Register is a collection of flip-flops. Okay, so if 32-bit data, 32 flip-flops make one register. Okay, so using basic gate, you can construct pretty much everything, all the logic on the IC chip. Okay, that's the basic things about logic design on IC silicon chip. Okay, I hope you enjoyed this video. Please subscribe.